All right, I think I did it. Cool. Next up, share screen. Screen 2. And here, the slideshow. Oops, don't quite have things the way I want them here yet, folks. Forgive me. Give me a moment. I want to use presenter view. Okay, let's try that again. Screen 2, share. Okay, I hope you're seeing my slide and not my PowerPoint program. Is that the case? Thank you for the affirmative. All right, each week we've had a fun and interesting icebreaker question. I suppose I should have had that up earlier. Let's come back to that. Let's do a formal poll at the end of where we fall in the coffee or tea question. But first, let's get through this week's lecture. This, like other weeks, will be recorded and available on our NIACS YouTube page. Welcome back. It's still the same of us as has been here through the training thus far, and we're delighted to share with you today's topic, that being monitoring and evaluating the effectiveness of adaptation actions. At the close of this lecture, I'll give a short overview of how to do step 5 using the Adaptation Workbook. And looking at where we are on this adaptive management wheel, we've been through all of the first 4 steps so far, defining our goals and objectives, assessing our climate vulnerabilities, evaluating our goals and objectives in light of our climate vulnerabilities. Step 4 was fun. That was brainstorming adaptation tactics, what those look like for your particular projects. Now here is the week where we're going to think of how to monitor to evaluate the effectiveness of our selected adaptation tactics. And as part of this, we'll also cover how to export your workbook as a PDF document so that you can use that to communicate all these steps that you have taken and show your intentionality to the various people that have an interest in that. This is also a good time to consider whether or not you would be willing to become a demonstration project. So you have been using the Adaptation Workbook quite a bit, but on the sister site, forestadaptation.org, there is a map of a subset of the projects that have used these resources and been willing to serve as a model for others to be formal demonstration sites in our adaptation network. And that's something you can take up with your individual NIACS point of contacts, which is the other thing I'll say about this week. This is a week when you are encouraged to connect one-on-one with your NIACS point of contact. And feel free to reach out to that point of contact if you're not contacted first. Okay, so before going into more detail, I'd like to share a few thoughts on monitoring in general. Monitoring is really about asking the right question to answer whether your actions are achieving their intended effects. In light of that, it's important to be very clear about what you want to learn, asking the right question. The question that you're asking depends on what kind of monitoring you're going to use. And summarizing 4 different kinds of monitoring here, I would say that implementation monitoring is in many ways the simplest case, although really no monitoring is simple. Implementation monitoring just answers the question, did we do what we said we were going to? Which might seem like a really low bar to clear, but when you think about, especially those of you who are working in an institutional capacity of some sort, institutions outlive people. Institutions have a lot of processes and protocols, a lot of things that have to go right for a set of actions to even occur. So implementation monitoring of whether or not you did the project you said you were, that's really important. It allows you to document who did what. You know, what are the important things that a person will need to know in 10 years or more about how this happened. A second type of monitoring is impact or response monitoring. It is primarily intended to describe change over time, but not necessarily in a cause and effect context. It consists of repeated measurements done to a specified standard. It collects a specified kind of data repeatedly over time, but it's not with the intent of ever analyzing those data statistically, for example. It says, through inventory surveys of a forest, for example, is stocking density changing over time? Effectiveness monitoring is another type of non-statistical monitoring. If you defined a desired effect at the outset of your project, effectiveness monitoring tells you, did our actions have that desired effect? And to some extent, they tell us how well did it work. This type of monitoring is usually designed based on some understanding of the system and how an intervention in that system would produce a desired effect. So say you have a project and you're concerned with water, climate change, recreational infrastructure. You have a project where you decided to install berms to slow the overland flow of water. Well, in this case, you would define a time frame and a metric and ask whether water movement has in fact been slowed by your intervention. And the last of the four types of monitoring I'll talk about is scientific research. A lot of us work for educational institutions in some way or another, or we partner with them that might be able to provide some capacity for monitoring. Scientific research as a monitoring tool doesn't necessarily start with a question or a hypothesis, but what sets it apart is that there is an intent from the outset in using statistics in some way to track trends and uncertainty. This kind of monitoring is probably the hardest to pull off most of the time in adaptation planning because it requires a lot of capacity. But I will say when it is done, when you can pull it off, it's really valuable because it can be predictive to other situations, and it can produce farther reaching insights than just a internal project contained kind of monitoring. So in the context of the Adaptation Workbook specifically, moving now into more detail than those general thoughts on monitoring, our main task this week is to consider what monitoring options you have in place and whether those might need to be modified to better capture the outcomes of your adaptation actions. That might mean adding new monitoring efforts. That might mean augmenting existing monitoring efforts. But regardless of what we choose to do with those, the point is to go around that wheel of the adaptive management cycle. We want to collect information so we can learn from what we've done and decide in the future whether we need to modify it. All right, so we do this, we design a monitoring plan, first of all, by defining a monitoring variable. What is the metric of the ecosystem or the project that you're going to measure that will tell you whether you're achieving your management objectives? What metric are we going to measure that will tell us when we have reached an important milestone on the way to our eventual goal? When possible, it's desirable to select monitoring variables that will also help you understand whether your adaptation tactics were effective in working towards your management goals under climate change. So it isn't just, is this thing working? It is, are the actions we have taken producing some benefit in better helping us adapt our project to climate change? One example here, when we see tactics related to the establishment of future adapted tree species, you might choose to monitor the survival rate of the planted tree seedlings. And it might be different from standard surveys, say of ground layer composition or forest inventory, because you want specifically to monitor at a higher density or more frequently because the things you have chosen to plant are outside of their current range. It means you already have some kind of monitoring going on that looks at the ground and what's growing out there, but in the context of collecting information about the climate change component, you augment that existing effort to capture the more climate change relevant information. The second step after you have identified a monitoring variable is to be clear about what criteria you'll use for evaluation. And that includes thinking about the measurement units. Are you talking about percentage survival of individually planted tree seedlings? Thinking about the units helps us to set thresholds that define success. And those thresholds may change over time. 60% survival of tree seedlings, that's pretty good, very good within the first several years, but that would be unheard of if you're talking about 10 years from now. Survivorship of tree seedlings in the forest being what it is. So this is giving us the power to set a threshold value and define success, but also encouraging us to think about how we are going to do that monitoring, over what time scale, who's going to do it, and so on. So that's the third component of designing a monitoring plan in terms of saying how you're going to do this. You might, if we're going to carry through with this example about tree seedlings, you might measure every year for 5 years after planting because you doubt the appropriateness of some of your species selection. So you really want to be there to collect high frequency response information about, maybe one of your species did great for the first 3 years and then you got a late cold snap in the fourth, and that killed all of one of your species. That higher frequency of monitoring would help you to capture that. Excuse me. Cough drops only do so much. And I cannot see your faces or hear anything from the group. So please speak up if you have, if I'm missing important questions in the chat, for example. One thing I'm going to say about designing the implementation of your monitoring plan, this is a good time to think about how you might be able to take advantage of partnerships with community groups, user groups of your sites or of your project areas, whether you have the opportunity to tag onto related efforts like monitoring networks that are focused on the kinds of things that you want to gather information on. Cooperative networks, academic research projects, regional resource partnerships, these are all the kinds of entities that have an interest in and sometimes a capacity for monitoring things that fall in their areas of interest, which may align with what you're looking to monitor. Okay, and now a few examples from past adaptation workbooks in terms of putting these 3 ingredients, the monitoring variable, the criteria for evaluation, and then the implementation of that monitoring. Here are 3 examples of how these 3 have been put together in some other projects. We've had projects that looked at invasive species abundance, kind of a general goal level statement about something that matters, and then the criteria are a bit more specific in terms of identifying areas for invasive species control and then surveying them annually to document whether those areas are coming in below the 20% cover of invasives threshold. Another example, oh wow, yeah, did I say 3 examples? Because you get 4, all right. Another monitoring variable, regeneration success. Probably a lot of folks working in forest environments are going to be interested in this one. Criteria for evaluation used by one project of more than 0.5% of desirable species in that smallest size class of the regen layer, and that assessed via periodic regeneration surveys after harvesting treatments were done. Another example, looking at forest canopy cover and maintaining at least 60% cover across riparian areas and assessing that on a 5-year basis, because that would presumably be a little bit slower to change than something like the coverage of an herbaceous annual plant that might be an invasive, or less subject to change rapidly than the composition of the regen layer in the forest. And one more example, again, from a watery context, like this riparian areas, a monitoring variable looking at the suspended solid content of surface water, and the criteria being a reduction of TSS below current levels, assessed every month for the first several years, and then every year thereafter. And what I want to say now is I want to return to this figure where we connect the dots. You have seen this one a few times throughout the training. We start at the top left and move down to the bottom right. We go through this iterative and intentional process of defining what our values are, looking at the threats to those, adapting our plans, and coming up with specific actions to adapt those plans. But it goes back the other way. As we finish our monitoring plans, we want to make sure we have metrics that can measure the effectiveness of our adaptation tactics. And in turn, we will use that to describe how we'll implement our strategies. We think back up this connection of the dots in terms of showing how our selected actions tier back up to the management challenges and opportunities that we've identified, the direct impacts of climate change upon our systems of interest, and then accordingly how those fit within the goals and objectives that we set out at the beginning. And monitoring down here at the bottom is the thing that ultimately helps us know whether we're on track to meet those goals and objectives, and whether or not we need to change to do so. So for the next part, I'm going to go into a little bit more detail from several projects that I've been involved in, and just share with you a bit richer detail about how we design different types of monitoring for different purposes. All right, the cough drop is gone, folks. So now it's now hopefully I can keep it going here. The first of the examples that I'll draw on is from a climate adaptation experiment called the Adaptive Aspen Management Experiment. It had a scientific design, but it was also an operational scale timber harvest on university managed lands. So it ticks a number of boxes in terms of things that I'd like to talk about, have talked about. One of our project goals with AAME, as I'll call it for short, was to evaluate management impacts on soil carbon and related soil properties over a range of timescales. And in the short term, we wanted to quantify how the timing of harvesting influenced the degree of soil disturbance. I'll note here, because I think it's important, that we actually wanted some soil disturbance on one of our treatment units. That was a unit that's pictured here, being cut in September, October of 2019. This unit, we aligned with the resistance way of thinking. We wanted to resist the impacts of climate change by regenerating aspen birch cover type. That's a cover type that's predicted to fare rather poorly in this part of the world. But we knew that birch in particular, although it's a climate loser, regenerates much better on a mineral soil seedbed. So in this case, we wanted soil disturbance, which might be to the detriment of carbon, but because it was important to a different goal and objective, and that being the successful regeneration of paper birch. And I think that all of us should consider and use the workbook for its ability to lay bare those instances in which we have co-benefits versus trade-offs. What we did in this case was some scientific research to support our monitoring. We wanted to be able to quantify the effects of these different timing of harvest operations on minerals on the soil surface. And we collected that data in a way that we could both quantify the magnitude of management effects on soil properties and also their variability. And what I'm showing you here are two different metrics of soil disturbance. The graph on the left is the percentage of sample points that had exposed mineral soil. And on the right, we have the percentage of sample points that have ruts. And both of these being a result of the tracked equipment that you saw in the last slide. And on the bottom, we're looking at 4 different treatments that are defined by when they were harvested. Mineral soil exposure, I've included reference lines here for 0% of sample points, and then also 15% of sample points. 15% is a rule of thumb for aspen birch forestry in the lake states that the Forest Service often uses. We know we're doing okay if we're below 15%. Maybe a different way to say it is usually operators and timber sale prescriptions can keep soil disturbance below 15% of the harvest area. And the particular season year that this experiment was cut, it was a heavier and denser, thicker snowpack than usual. So we were able to look at the timing of harvest relative to that the loss of the snow in April of that year, and see how really with snow cover present, there was little to no soil disturbance, and with snow cover gone, there was considerably more, statistically significantly more soil disturbance. So that was an example of how we designed scientific monitoring to support addressing a project monitoring variable. Another example from the same experiment, not scientific research, but response monitoring. We wanted to look at sapling stocking levels after the treatments, after the different cutting treatments. And there were a variety of different cutting treatments. We did a kind of monitoring here that was relatively quick and very informative, but not statistically testable. So I'll share with you a few results for that. This table here shows 5 different conditions. Reference is just an unmanipulated 110-year-old aspen-dominated forest. This is the control that we compare to in this study. Mid-rotation, this is data collected in a number of approximately 40-year-old mid-rotation past aspen birch clear cuts. And then we have 3 other treatments that constitute the adaptive aspen management experiment, those being a resistance, a resilience, and a transition treatment. Resistance, as I mentioned, was where we were trying to resist the effects of climate change and maintain a climatically vulnerable forest type, aspen birch dominance. Resilience was where we wanted to design treatments that would maintain a still aspen dominated condition, but with a greater degree of structural and compositional complexity than was present prior to the experimental treatments. And then transition was where we designed a prescription to transition away from aspen and towards a composition dominated by longer-lived northern hardwood tree species. And then the 2 columns in this table are the number of stems per acre of Poger, Populus granidentata, or big-tooth aspen, the dominant species in the overstory. Excuse me. And Fager, Fagus grandifolia, American beech, number of stems per acre. And the condition you see under reference forest, this is a 110-year-old mature aspen-dominated woods, not surprisingly, you find 0 aspen in the understory of this small size class that we were monitoring for with our sapling stocking surveys. On the other hand, a lot of advanced regeneration of beech in the understory of those century-old aspen woods. Mid-rotation condition, 40-year-old aspen, we're still coming up with some aspens in the understory, but they tend to be larger and much fewer in numbers than we see in the recent cuts. So this again was 2 years after cutting was done. And we're looking at thousands of aspen of that sapling size class in the resistance, resilience, and transition treatments, and just hundreds in 40-year-old aspen stands, where these sapling aspen, so to speak, what those really are is just dying overtopped individuals that are on their way out due to self-thinning. And you can see that the operations in these cutting units, the resilience, transition, resistance, really knocked back that beech density as well. So one thing that I'd like to draw your attention to in this slide is the number of aspen per acre for those 3 different cutting treatments. And thinking through when that cutting was done, the resilience and the transition units, those were cut in the springtime on a snowpack that was either fully present or maybe starting to diminish. But recall that I mentioned the resistance treatment, that was a fall harvest. So that was a growing season cut. And we have much reduced aspen regen in that cutting unit. This did not surprise any of the forestry professionals involved, because they understood and knew from experience well that when you do a growing season cut on aspen, you get delayed aspen regen. But it was also not an intentional outcome of doing that fall harvest. What it did do was result in a much lengthened and more pronounced increase in soil moisture. And that is the other graph I have on this page. That's the graph that I have on this page. You can see these are time courses of soil moisture content in the top 30 centimeters of soil for either the reference, that's the blue dots, I think, I can't see from my screen. The reference and the mid-rotation are basically the same. Those are the blue and the pink dots. Prior to cutting, the resistance unit was not any different. It wasn't anything special, but doing that cut during the growing season and delaying the aspen regen got us basically a second full growing season of elevated soil moisture, which is the sort of thing that we learned from this experiment that we can then take back to through scientific communication and help people think about how to employ tactical decisions like that when you do the cutting, with an eye towards how that's going to influence your desired future condition. Paper birch was something we really wanted to get a lot of regenerated. So we went with the growing season harvest to cause soil disturbance. That had the result of diminishing the amount of light competition from big tooth aspen, much less of it rebounding under this resistance treatment, and keeping soil moisture higher for longer. Drought being the principal climate change impact on paper birch in this part of the world. The last monitoring example I'm going to talk about is another example of scientific research. I'm going to share it here, just hoping that it's interesting to enough of you as to make it worthwhile. This is going to be the most informationally dense example I provide. We started with essentially the same kind of forest composition, about 100-year-old aspen-dominated forest, again in northern lower Michigan. In this case, this was not a management experiment. This was an ecosystem experiment in which we wanted to accelerate the ongoing transition of an aspen-dominated forest towards a forest dominated by longer-lived, later successional tree species. And in this case, the monitoring variable that I will be showing to you is net ecosystem production, or NEP. That's really the thing that everybody wants to know who cares about forest carbon is it coming in or is it going out every year on balance? So NEP tells you if you have a carbon sink or a carbon source. This was an experiment that we initiated, well, 15 years ago this month, actually. Yep, and the monitoring has been ongoing since that time. And what we've learned has been some interesting things. I'm going to draw your attention to just one of these figures, top left. This is NEP, this is the net carbon balance. So the first thing to notice is that over time, we have forests, whether control or treatment, so whether left alone and just monitored, or all the aspen were stem girdled to accelerate their demise and transition to a later successional forest type, we have a reliable carbon sink, storing on average 2 to 3 megagrams of carbon per hectare per year. The thing that I'd like to point out is the degree of interannual variation present in both the control and the treatment stand. But also looking at that treatment stand, which started with a basically parallel but higher level of carbon sequestration. Unclear why, maybe some difference in soils or proximity to Douglas Lake and its influence on the microclimate. But we knew even before we conducted the manipulation that this treatment area where the aspens were going to be girdled was somehow a little more productive. And basically the two stands tracked each other for several years. Girdling happened in 2008. That system crashed in 2012. Something really big happened in 2012. NEP dropped lower than it has ever been in that area, but then it rebounded in a way that it's starting to pull away from the control condition. And this is the sort of thing that we would not have known about if this was not a scientific research study. Neither would we have known the why of it. And I'm not going to talk about it, but other figures here and other science that has been published out of this site has shown the reason has been the replacement of the live fast, die young lifestyle of aspen, which has low water use efficiency, low carbon use efficiency. Aspen being replaced by those longer lived, slower growing northern hardwood species, oaks, maples. That's what has shifted the functioning of this forest canopy and caused it to become a stronger carbon sink with the loss of the short-lived species. Now is the time I'll stop and ask if there are any questions about the materials that I've covered so far before we spend the next 10 minutes or so going over how you use the workbook to develop your monitoring plans. So again, with my screen configuration, I can't see if anyone is raising hands or asking questions in the chat. I'll ask either for one of my NIAXers to call it out, or if anybody wants to come off mute, please do so.
Yeah, sure. Thanks, Luke. That was really great, especially since I know you're a little bit under the weather. So I really appreciate that. It looks like there's one question that says, could you discuss standard deviation? So maybe you could take like a non-technical approach to answering that question.
Yeah, well, I think I'll try to be non-technical. I'll raise that non-technical and say, let's just talk about uncertainty generally. There's a variety of different ways you can measure it: confidence intervals, variance, standard deviation, standard error, you name it. A lot of the monitoring that many of us do in an operational, daily work kind of a capacity, probably most adaptation projects don't quantify variance, don't quantify uncertainty. We collect data in some way that tells us maybe directionality of an effect. Is there more or less regeneration because of this action or these example tactics? Maybe it gives us magnitude in addition to that directionality. It says, oh, we think that taking adaptation action X results in a 10% increase in, germination, but adaptation action Y gives us a 40% increase in germination, some variable like that. But to collect data in a way that allows you to quantify uncertainty in addition to direction, magnitude, that's in a lot of ways the most powerful and often the most disappointing, because you will see that trends that you think which look quite clear in terms of directionality and magnitude, they really become much more meaningful when we can say how much uncertainty there is in that trend, how much variation there is in that response, and becomes all the more powerful if we can tie that variation to something else we know about a system. If we have 10 different monitoring plots and we know something about their soil texture, and we see that in fact, the difference in germination success of a desired species is not due to the adaptation action so much as it is to soil texture, that becomes a very different takeaway than if we had never assessed that range of variation, whether through standard deviation or otherwise, or looked at what might be explaining that variation. I hope that was satisfying.
Thanks, Luke. Yeah, I think that was great. And just to perhaps restate in other words some of what you said, I think capturing that variation, whether you're measuring standard deviation or some other metric of variation, is particularly important in the scientific monitoring. But in a lot of other cases, and so it's particularly important because a lot of time for the scientific monitoring, you're trying to take like a small sample and then scale that up to like perhaps multiple sites or like a bigger site. But in a lot of cases, if you're doing a monitoring for a pretty small site and you're taking perhaps qualitative data for your whole site, you might not be able to quantify the variation in what you're seeing, but it might be pretty clear. Like you can see the difference that you're getting significant, like ecologically significantly more native species, let's say in the understory. Even if you aren't really quantifying it, you're not assessing like how much variation there is in your small estimates, you're ecologically able to observe that there is a meaningful difference. So I don't know if that's helpful. And in certain approaches to monitoring, capturing that quantitative variation might be really important, and especially for some of the work that Luke presented. And for some of your projects, capturing that variation might not be quite as important. I don't know if that's helpful or not, but thanks, Luke. I thought you explained that well.
Thanks. Well, we can just racquetball this back and forth. I don't know, I'm not good at sport analogies, but you said some things that I would like to then respond to. I'm really glad that you talked about the need of whether or not to quantify that uncertainty. I don't want to suggest that monitoring doesn't have value if it doesn't quantify uncertainty. There's no reason to hold your monitoring plan hostage to scientific research. By all means, monitor. Even a monitoring plan that doesn't quantify uncertainty but gets done reliably over a long period of time is probably more important and more educational than a scientific study that lasts 3 years. So I hope people will not hear us scientists talking about uncertainty and think that, well, if I can't quantify uncertainty, I'm not going to bother monitoring. No, come up with monitoring plans that are repeatable and defensible, and the longer you can do them, the more valuable they get.
Great, thanks, Luke. Are there any other questions? Feel free to unmute yourself if you have one or type it in the chat. Yeah, Alan?
80% of Vermont is owned by private landowners, fairly small acreages. If adaptation is going to trickle down to the mass of the land, I'm not sure how, and the ownership is only the life cycle of the individual landowner. And so how is adaptation tactics going to be effectively monitored for effectiveness in this scenario?
So if you have a scenario where a project is responsibility for a project or a property on which it exists is going to transition to someone else in the future. And you asked about monitoring as far as that goes. I think that's an example. It may as well be an example of an institution. It need not be a family woodlot. In either case, the most important aspect of monitoring is documenting how it's done, so that whoever is responsible for that project, for that property in the future, understands what was done so that it can be repeated. In terms of the bigger picture, the ownership question and adaptation, those are great questions. I think find themselves a home in our next week lecture in terms of communicating on climate, communicating on adaptation. And we could point to some examples, in fact, of past APO participants like Tim Stout of Northam Forest Carbon in Vermont, and efforts that he has made to carry that conversation more widely to individual landowners about climate adaptation. All right, let's take the next step of talking about the adaptation workbook itself and how to do this thing of developing a monitoring plan. The next steps for your week ahead include doing that monitoring plan, completing a 5th homework assignment, and figuring out how to export and share your plan, both for yourself in the future you, but then also for stakeholders, for other people at your institutions that you want to share all this thinking you've done, all this documentation as part of planning processes that you might be using in your organizations. So in terms of developing a monitoring plan, the first thing that you'll have is the sidebar has, under step 5, monitoring plan, you'll start with a blank slate. The blue arrow here shows you the big button to click on adding a monitoring variable. The little drop down carrots, V, triangle things at the top have links to a variety of resources and videos and so on about monitoring plans. If you add a monitoring variable, you will get a dialog box that has the 3 components that I talked about in this lecture. It asks you to identify the monitoring variable that you'll use, what criteria for evaluation will correspond to that variable, and then last, implementation. How are you going to do it? For each monitoring variable that you add, there will be radio buttons to select whether it does or does not apply to specific objectives. Sometimes you'll want to have monitoring variables that apply to different objectives than others. There is a homework assignment for you to complete, and a few instructions on how to export your plan. You're gonna want to use the print feature, in this case, print current version, and then you'll get a notification of formatting for landscape orientation, and your print is actually going to be to save as PDF. You can, of course, print a hard copy if you want, but currently the way that we are able to support the export of adaptation workbooks is via PDF documents from the interface. All right, so looking ahead to the next week, please check in if you need to with your NIACS point of contact. Let them know if you need help with some particular aspect of the workbook or a brainstorming discussion. Looking ahead to next Monday, we'll have that lecture on communication strategies for talking climate change. And next week will also be a discussion week. So be ready to talk about your step 4 adaptation tactics and your step 5 monitoring plan ideas with your regional discussion groups next week. And that concludes this scheduled programming. I'll stop the recording. If folks